So welcome back. We will continue with the parallel axis theorem, and then we'll do perpendicular. So here's an example which I've solved last year. You can have a look at it and try to solve it. Here's another good one for you to do. Here's another one, and I'll just talk to this basically. Obviously, you'll do it, and I want to do one in particular and show you what you can focus on. For instance, one like this, you can see that this bar over here, the side bars here, two side pieces, um, that is perfectly fine. However, if you look at these two end blocks here, which is made up of copper as a state, there one has to adopt the parallel axis theorem, obviously at a distance of 300. Similarly, over here we've got these bars attached to the thing, and Nosipo, I think, was worrying about one of these questions. Obviously, you have to now relate this bar to that center within. Obviously, that center will be the inner radius, sorry, the outer diameter or outer radius plus halfway the of this, whatever the distance of these bars is, or the thickness of those bars. So that's a classical one. This is the one I want to do. Here's another good one. All of these are easily examinable questions, and like I said to you, make sure you're always able to work with the percentage and your torque required, right? Obviously I'll add that. Here's another good one where we have you got your outside thing, you've got a shaft in the middle, and we've got two things. So I put up a few problems here. There's even one with your basic perpendicular one. On top of that, I've obviously posted some tutorials and stuff for you, and I just want to bring attention to one, and the ones you should actually focus on as well in your notepad. What's important is that you're able to solve all of them, and then obviously you never get one of the procedure is the same. That's what I'm trying to say to you. Um, but if you can practice those, you should be. I mean, you'll be well prepared. And I just want to share, and it's definitely the first question in your test. I want to share this, and what I'd like you to do, but I'll mention it again. This one problem is an absolute must. This guy as well. Try doing this one. This one as well, which you'll do. Try this one as well, and that one as well. So that's four main ones. 1, 2, 3, 4, 5. Those 5 as well. Plus the other thing I've sent to you is an absolute must. What I'd like is for you guys to try to do number 2. Obviously, after the first practice I want you to do is number 2 after the lecture, obviously, or during the week. And obviously the rest is on you. I'd like to see everyone try that one. Okay, so let's move on, continue with the parallel axis theorem. I think I've explained it well. And I wanted to try this one quickly before we go on perpendicular. Okay, so here we have some kind of body, a cast iron roller apparently, and we're required to find the mass moment of this particular object. And I'd like to ask you guys, what approach will we take here before we actually start? Sorry about that. What are we going to do? I want to see if everyone is thinking in the right space, basically. Let's engage, students. What will be the first step? Let's talk there. I'll give you guys 2 minutes. If not, then I'll just move on. Mass of the main cylinder. Yes, that is correct. Thank you, Mr. Duplessis. I'll find the mass on the full roller. Fantastic, right? Okay. Get the mass. Perfect. My next question is, what do we do with these 2 holes? What's the next step after that? The mass of the main cylinder is fine, right? Everyone can get that. calculate hollow areas and subtract them. Mr. Breed, Mr. Tape, that is Prof. Breed. Yep, and Prof. Bukawana. Yeah. But now the thing is those holes in, how are we going to find the mass moment of those holes? Who has any idea? Mr. Kitongo, Casimiro, Yavanga, parallel. Ah, yes, exactly. You have to use parallel access theorem. That is correct. Dr. Duplessis. Yep. Okay, sir. Yeah. Anyway, should we give it a go? Or can I move on with the other part, the last part of the lecture? Okay. Yeah. Cool. So I'll just do 2 more examples, and you can play around with the rest here. But like I said, with your preparation, as always, it's all possible, right? Everything with the scope I give you, practice over the lectures, you'll be able to master this. Yeah, Mr. Duplessis, we can move on. Must we do it or must we move on? Yeah, do it. Okay, okay. Yeah, I'll do it. All right. Just preparing the whiteboard. Shouldn't take us too long, hopefully. Let's see. Okay. Then we can close off the section. Okay, so first is first. We have to work out the solid portion of this thing, right? And let's begin with that. Mass, let's call it solid in S. In subscript S, make it smaller. Let's make sure I'm sharing. Okay, my pen is in the way there. I'll remove that now. Okay, fine. Cool. So that's fairly easy. It's 750 in total. So it's pi. The density is 7,200 times pi over 4 times 0.75 squared times that total length of 1.4. Okay, can someone just give me that mass quickly? And that'll be the solid portion. Right? So we need a mass there. Is that correct? Hey, where's my calculator? 7,200 times pi over 4. 0.75 squared times 1.4. Okay. Yep, that is correct. Nice. Okay. So what we can do now is find the mass moment of inertia, right? That's the next step. Obviously, this is a complete solid. That's 4,453,207 kilograms, or 278 if you want. We can find obviously the mass moment of that, and that's 4,453.208. And then diameter 0.75 squared, and that's divided by 8. Okay, so let's get that rotational inertia of this guy in kilogram meter squared. 313.116. Thank you very much, Muda, for being very active today and fast. And that is fine. So the next step is to work out the hollow parts, just like Prof. Duplessis says. So we have to work out those two small circles. So we're going to call it I, or let's say mass hollow first. Mass hollow. And the diameter is that 300 over there? Yeah, it's 300 millimeters. So that's going to be the same material, 7,200 times pi over 4 times, what's it, 0.3 squared times, what's all the length was 1.4. Right. Okay, let's get that mass as well. In kilograms. Cool. Let's see. 712. Yep. 712.513. Okay. That's fantastic. Thank you, Sipon. 712.513. Yeah. Okay. 712.513. Sorry. Yeah. Next is to find the mass moment. And fortunately for us, it's also just another solid. So we can say I hollow is going to be 712.513 and the diameter 0.3 squared divided by 8. What do we get? Kilogram meter squared. Uh, 10.0186. What's it? 8.16. Okay. So obviously we found that about what axis? No, it's too thick. About this axis here, right? But we are rotating through ZZ.
Screen is not showing, sir.
Okay, can you see it now? Not sure what happened. Thank you for that. And so as I have here, we found it through that axis, or you can call it GG, the centroidal axis of the hole, but we are rotating through ZZ. So can you please tell me what are we going to do next and what is that distance? Okay. So next step, guys, we have to use the parallel axis theorem, obviously, to relate it to ZZ, but I'd like to know what is the distance. Fantastic, it's 150. Yep, these guys, they've got it, man. Once you master this, you kind of master the whole thing. So IZZ, sorry, of the hollow section is going to be 8,016 plus the mass 7.12513 times 0.15 squared. And if you do this, what do you get? I'm working it out with you now. You get 24.0473 kilogram meter squared. You guys agree? And what's the next thing we need to do once we have this? Mr. Casimiro, what is the next thing? But the first, oh, let's the whole chat. Sorry. So obviously over here, this is for one hole, for one hollow, and then we have to times it by 2, and obviously we'll get an answer of 48,0946 kilogram meter squared. All right. So then to find the total for this cast iron roller, it's going to be, let's go to it. Is it 313.116 minus the 48,0946. Nice. Okay. Are we all happy with this? That's 265,0213 millimeters. You can find the radius of gyration yourself. Yeah, fantastic. So you can find the radius of gyration. Just don't forget to subtract the mass from the previous thing. All right. So I hope you all got that. That's just another way of using the parallel axis theorem. We sometimes, and obviously that's going to help you with one of the problems I've mentioned, especially the ones with the holes. You know, you have to subtract that from the actual thing. Okay. Is there any questions before I move on? Any questions? Any questions, students? Oh, fantastic. Okay. I guess everyone is, I'm not sure where they are today. Anyway. Okay. So I'll just move on. Nothing. Thank you. Thank you very much. Okay, so we're heading to the end. Okay, so the next and the last part of this, which is very uncommon. 80% or 90% of the work is related to typically all the problems we've done before. However, obviously, this is some of the content which I have to cover and I will cover, and I'll show you exactly which tutorial speaks to this, right? But like I said, it's typically, if you're doing the reassessment, you might see one of these problems. However, for the main tests, for the tests and the exams, it's one of those, you know, it's more unlikely. So rather, you can do your parallel axis theorem with all the other combinations, you'll be more than ready for, you know, yeah. So what the perpendicular axis theorem essentially talks to is that if you have your x and your y axis, I don't know if have you guys done torsion yet? Have you guys started already with torsion in strength of materials? Mr. Priat? Yes, okay, thank you, Mr. Gomez. Garcia, sorry. Yeah, so you get, yeah, so you get that thing called J, which is your polar second moment of area. And by the way, like I said before, this here is your resistance to rotation. You're going to see in strength of materials 3, you're going to get bending, which is I, which is resistance to bending, and J. The J you're going to be getting, that the J you have in your torsion formula is your resistance to torque. So it's obviously an object with a big amount of J has higher resistance to torque. So yeah, I'm just letting you know now. And all this essentially, the perpendicular axis theorem is that if you want to find for instance, they say that the sum of, okay, if you have your x and you have your y, and you basically want to find it about an axis perpendicular to those. So if you're looking at this figure over here, you can see we have ixx, which is basically your m, your 12mb squared, right? Then your iyy, obviously this is for a thin plate. You have the half ma squared. And what happens if you want to rotate, about obviously the zz axis? Obviously we've done that before. It's going to be simply be basically adding your ix and your iy. You just literally sum them up algebraically, the ix plus iy over there. Now, if I take you back to these formulas, right? Let me have a look. You can see a few parallel axis theorems happening over here. So we have ix over here and we have iy. So ixx is 6 pi over 16, and we have pi over 16 plus pi over 16. If you would add ixx to iyy, what are you going to get? So it's basically 1 over 16 plus 1 over 16 will be, Mr. Breed, can you please tell us? Students, I hope you're following me over here. Can you guys see there? So if you take ixx, it's not 1 over 32, it's 1 over 8. It's not double. You add in 2 16s, so give you 8. Prof. Duplessis, I think you should revoke your professorship. Yeah, 1 over 8. If you do exactly the same with, we can even do your hoop over here. If you add these two here, that's mdl plus mdl squared plus another one, you should get the same. If you do this over here as well, you'd probably get the same. And even if you do for the cylinder over here, so it'll be ixx plus this iyy. Oh, well, yeah, you should get the same. So, oh, sorry, ixx, ixy, and give you the, oh, sorry, you get iz plus iy, you should get ix. And if you do this here over here, the x and y, you should get z. But in this case, it's the same about any for sphere, for a solid sphere, that's all the same. So that is how they essentially get these axes by using, or especially per perpendicular axis, they use this is how they use the perpendicular axis theorem. Okay, so it's not difficult. It's just a matter of relating one axis to this one. So this is a cool one. I'll tell you why I like it. We are required to find at BB, right? So this is a thin rectangular plate, 600 by 800 by 60, and obviously we can either assume we can make it a thick plate, or we can make it a normal, a normal type plate. We can use a normal one. Obviously, the shortcut is to just work out IZZ and then relate it to IBB. So it's quite simple, but the whole exercise of this is to use your IXY plus your IY and then get your IZ and then get IB. Similarly over here, which maybe we should do this one. And over here, they want us to get IBB. So we need to get IYY and then IXX, but obviously we have IZZ for a disk. Oh, no. So we have IZZ and we can get IYY, and then we have to subtract IZZ minus IY, then we can get IX. And obviously we can relate IX to IB. So I think we should actually try to do that. Don't you think so? That'll be a more fun one. Yeah, so let's rather do this example compared to that one. Okay, so that's the last example for this. All right, let's just take it. We can just duplicate this over here. Okay, so let's start to do this one. Just copy this. Just going to place it on one slide. Can we use the parallel axis theorem instead? Yeah, you can. You're gonna have to use parallel axis theorem. That's the thing. That's what I'm saying. It's more. It's really an add-on question. It's not. It's the parallel axis theorem is obviously way more powerful than this thing. That's just a. So I'll show you what I mean here. Okay. So first step. The objective of the question is obviously to get to IBB, right? So let's find IZZ, right? Let's get IZZ. IZZ for a disk in the center, if I remember correctly, will be shouldn't that be md squared over 8, I think. Yeah. So we have md squared over 8. Then obviously our IYY for the disk is M16. So IYY is basically it's more of the same. This is not difficult, just an extra thing which has to be taught essentially. So that's 16 over there. So if I take the mass, don't have to really work out the whole mass now, but anyway, so it's going to be 8,400. It's brass. Pi over 4, 0.6 squared times the thickness. It's 10 more thick. Obviously, we have to say 0.6 squared over 8. And obviously, you have over 8. This is it'll be half of that there. So we say I thought it's 8,400. We could have just used IXX. You know what I mean? And then related. So it's more of the same. But you'll see when it gets fun, man. But like I said, it's really an add-on kind of thing. So here you'll get 10,68. I hope I didn't make a mistake. 0.6 diameter. Let me just make sure. Maybe I missed a 0.6 squared. Oh, 0.01. That's what I thought. Yeah, I had a feeling I slipped something there. So it's 1,069. 1,068. Yeah, I want to say 9 maybe. And obviously IYY will be half of this, right? So that's basically divided by 2. IYY is basically, you can see the IZZ divided by 2. It's nearly the same. 0.534 kilogram meter squared. And then we're subtracting to get IX. Remember that IZZ should be equal to IYY plus. Yeah, so obviously we start subtracting the 2, which is basically half, and then IXX will just genuinely be 0.534 kilogram meter squared. And once you do that, obviously we have to relate that 550 millimeters away. So like I said, it's a very small thing within this thing. However, there will be a fun tutorial, and I'll show you now for you to do. Like I said, if you plan to do the reassessment, make sure you do that. And I'll give you an example of what I mean. So this is part of the one note I gave you, but this one uses parallel axis theorem, right? That question. And then the last 2 questions is basically this one over here, which is a cool one, where we have to find IZZ. And then obviously there's IX and there's IY, and you can find all of those things. And then there's question 3 over here. We have a plate and it has different axes. It's also part of the other top, but I just thought I'll separate them for you. Okay, guys, all I can say is well done. You made it to the end of the chapter. I have to repost the slides because there's new other things. Is there any questions regarding mass moment? Before I move on.
Yes, sir. So you went very fast through this parallel theorem. I don't really understand it. You're adding your
perpendicular axis.
Yes,
you did the perpendicular axis.
Yeah. Yes.
Go for it.
No, I just don't understand what you're doing. How are you adding these axes and things like that? I don't get it.
Okay, cool. So I'll just go back then. It's fine. It's no problem. So I think what I'm trying to say here, first of all, the first point is that the formulas on this particular table, right? They come from like Ix plus Iy will give you Iz. That's like the first point there. I hope you're following on that one. Cool. So what do they have on the formula sheet for assessments? I've already posted the formula sheet. You can go have a look at it. So you have Ix and Iy. Yeah. So what I'm just saying is that they basically use the perpendicular axis theorem to get some of these formulas over here. Now, obviously, we prove that with one example. What I'm telling you, Mr. Duplessis, is that it's not like essentially you're gonna need it, but it's there. So, for instance, if you have Iz already, which you already have on the table, right? You can obviously just use the perpendicular, the parallel axis theorem to relate that to Ib. But the illustration was just that Ix and Iy will give you Iz, therefore you have Ib. Similarly over here, right? If you have Iy, you essentially have Ix because they're exactly the same thing. But I'll just show you if you had Iz, for instance, and you subtract Iy, you will still get Ix. Then obviously you have to relate Ix to Ib using the actual parallel axis theorem. You got that? So it's not like something which is, as I said, don't worry too much about it. Yes, Mr. Duplessis. Yes, that's correct, Mr.
I understand, because I mean I could have done parallel from the start, parallel theorem.
Yeah.
But this previous example, example 1, this axis BB is at a horizontal to the y. Go up to example 1.
X, you mean?
Example 1, so not example 2.
Okay, cool. Let me go back. This one over here.
Yes.
Yeah.
Now this is different. This is axis BB is it's not on the same plane as Z. Okay, it's in the same it's parallel, but it's at a like a horizontal, if that makes sense.
So you're probably thinking, how do you actually get this value? So if you can possibly use Pythagoras here. I don't know if you can see that.
Yeah, I can see that.
Are you with me? Yeah. So you can just use Pythagoras to get that distance from there to there. Yeah, I actually didn't think about it. It's possible, unless they're saying exactly they're giving the distance. Axis BB passes through one corner of the plate here. So yeah, will that be parallel to that? Yeah. Going to give this one a go. It's nothing crazy with the Duplessis. Don't overthink it. You know what I mean? I think I'm telling you that. Don't worry too much about it. Yeah. Like it's not so crazy, man. It's so the ones like I showed you in the other touch is more what you should actually focus on. Yeah. But that is correct, Musipo. It's always like that. Yeah. It's like I said, it's not always there. It's not a big deal. Like most of the stuff, if I can just show you the other touch. Yeah, for instance, it's not like you're not going to be using it. What's important is a parallel axis theorem. Like this one, for instance, right? Here we have
Hello, sir.
like this over here. Yes.
Could you please go back to the previous exercise?
Okay. Yep. This one.
Yes. Something we don't understand is that you repeat the diameter 2 times.
Where?
For our coordinate ZZ.
So ZZ is once there, right? D squared over 8. You got that?
Yes.
So then I'm saying I found Iyy, which is that over there.
Okay.
Yeah. So, but if you look at Izz and Iyy, you can see Iyy is half of Izz. If you divide this by 2, you get that. Do you see that?
Divide by how much?
What's 1/8 divided by 2? It's the 16th.
Okay, okay.
Yeah. And then you get basically IXX. Oh, yeah. Oh, sorry, you get IYY there, right? Which is the same thing. So what I showed you, IZZ plus IXX plus IYY. So by subtracting the 1,069 minus 0.534, which will get 0.534 again. Then all you have to do is use parallel access theorem to relate X to B, and then you're done.
Okay.
Yeah.
But here on top, 0.6 is the diameter, right?
That's correct.
But the end you still put 0.6 again? But how?
Because this is the mass. And that is the diameter.
You combine it.
Yes, I just did it one time because it's not a big deal.
Okay.
I don't want to spend too much time on something which is gonna confuse you guys. But once you do it, you see.
Okay, thank you.
Okay, no problems. So like I said, if you look at this stuff, for instance, you can see you're not going to be using perpendicular axis. It's all parallel axis theorem stuff, especially for those holes over there. Similarly over here, there's holes on those ends, which relates to that center. That's parallel axis. Likewise we did here. Something similar in this end because we have another piece away from the actual center of rotation. Over here, it's kind of there might be a parallel axis theorem over here as well. Oh, I didn't actually show you the other type. Obviously, I did post this already as well. I think you guys can see that. This is wall. This is also a spoke type example. Make sure you do this one. Again, parallel axis theorem over here. This is another parallel axis. So can you see perpendicular theorem is not mostly there. I'm just letting you know. It's like here's a perpendicular axis theorem question where, yeah, maybe this is a cool one for you to actually try to do. Where you can do IZZ, but IZZ, okay, it's obviously it's related to that corner over there. You can probably figure that out. And then if you have IXX, or you can find the plate on the end, and then you can start to relate that. So this is maybe one worth doing. It's uncommon. Again, parallel axis theorem, we got these bars away from the center over there. Similarly over here. Okay, guys. Just to show you I always kind of do examples which you should have enough technique to solve everything else. Yeah. Is there any other questions? Any other questions, students? Before we close this and move on to simple harmonic motion. So Sipo, Muda, Amanda, Mr. Briet, Mr. Sima, Mr. Cinegram, all good. All you have to do now is go play around and go figure the stuff out. That's all. You should be more than adequate. I assure you. Okay. So guys, what I'm gonna do now, I'm gonna close the session and create another session, and then we'll spend the last just need to attempt that perpendicular example. Yeah, I'm supposed to proceed. Do it and then let me know. Thank you. You will obviously have a solution there, so do it and then see. It's not difficult, man. As I'm saying, you'll be comfortable once you do it. But yeah, I'll stop this recording and then I'll share another link, and we have to start simple harmonic motion. And then yeah, and then it obviously won't be too rough. It'll just be introductory, and then we'll continue next week. Okay, so let me just stop recording here.